Eric Burgess here. Let A and B be two mutually exclusive events. Are A and B independent events? Mutually exclusive means that the events have no overlap. So here's the event A and the event B. They can't happen at the same time. For example, you can't have a true-false question be true and false at the same time. If you do, something's wrong. You can't flip a coin and get a heads and a tails at the same time. That's mutually exclusive. Now, independent means that the event A its probability is unaffected by the probability of event B. So there's this test for independence, A given B. If it's still probability of A, then that means that B did not matter. For example, the chance that you get a heads given that before you got a tails. Well, if you got a tails before, it still doesn't matter. The chance that you get a heads is a 50-50% chance. So probability of A. This is really useful if you do a study of two events, like let's say the event that gym memberships and how much weight you can lift. If you can lift above the average amount of weight, you would think that they would be dependent. So the answer would not be the probability of A. That you would think they'd be dependent. So you could do this study and see if this is true, and you could prove if it's really dependent or not, and by how much, right? So that's an example of independence. Coin flip would be independent. Now, when I say coin flip, it's two coin flips. So we say, okay, A and B mutually exclusive. Gotcha. Are they independent? Well, let's think about this. If they're independent, probability of A and B is equal to probability of A times probability of B, right? And if they are mutually exclusive, A and B can't happen. They have no overlap. There's no spot that's both A and B, so it has to be 0. So this would mean that one of these up here would have to be 0. But, for example, coin flip, it's either heads or it's tails. And the probability of heads is 0.5 and the probability of tails is 0.5. So A and B are not 0. And I should say here that I'm ignoring zero measure events as just a footnote. So because it's a trivial case. So we've got probability of A, probability of B. They're non-zero, which means that so this is for independence and this is for mutually exclusive, which means that if an event is mutually exclusive, it cannot be independent. So the answer is no. And this is why. It's a paradox to have it be this at the same time. Now, you might be saying, but a coin flip is an independent event, not a single coin flip. So when we did this was two coin flips. But over here, we've got a single coin flip where if you have a heads, well, the fact that it's tails directly depends on the heads. If this is 0.5, well, then I know the other one's got to be 0.5. Let's say that I had a coin that 60% of the time it was heads. Well, then the other 40%'s got to be tails. I can directly determine it if I know that they're mutually exclusive. Whatever remains has to be the other thing. And so that's how this works. So if two events are mutually exclusive, they cannot be independent. Another example could be like if it's raining versus not raining, that's mutually exclusive. The 70% chance of rain means there's a 30% chance that it doesn't rain. They directly depend on each other. So they are not independent events. So I'm trying to give just a couple examples to help you think about it. I personally had a hard time with the coin flip because I was thinking, whoa, that's this and that. But then I realized, oh, well, here I'm doing multiple coin flips where this is just at the same time, mutually exclusive at the same time. So if you have any questions about this, feel free to let me know down in the comments. Subscribe and hit that bell icon for future videos, and we'll catch you in the next problem.